Thank you, Neha, and thank you very much, Professor Ghosh, for the very engaging talk. Your talk today certainly provided some a very insightful overview into the photochemistry of eumenalin and the photoprotection mechanisms. And we have quite a lot of questions pouring in. And before proceeding with that, I would again like to thank Dr. Reshmi Thomas, my co-moderator, who has been helping me accumulate all of these questions. And without further ado, let's jump right into the first one. So in the beginning of the talk, you mentioned about how the primary sources of error in these calculation methods is due to failing to account for these multi-configurations of the frontier molecular orbital states. How much is the error reduced by accounting for this, and is this not accounting for the multi-configuration states the only source of error?
Multi-configurational part is really a major chunk of that error. So without considering multi-configurational wave functions, if you try calculating, especially these photophysics, you get qualitatively wrong results, not just quantitatively, but qualitatively wrong results. So yeah, so those are orders of magnitude error you will get with those. Because here, see, you are looking at the energy gaps. You are not looking at the base energies. You are looking at energy gaps. And even if there's like 0.5 EV, 0.5 EV is huge in kcal per mole. So that's, it's between something which is chemically possible versus not possible. So yeah, the errors are pretty significant.
Thank you. Next question, I guess you have already answered that in your talk, but if you would like to add something more is, why does melanin have a broad absorption spectrum?
It is because of structural heterogeneity. Well, actually, it is because of many heterogeneity. There are different monomers. The different monomers are bonded in different ways. Then they're packed in different ways. So finally, the chromophoric units are very different. And so there's one chromophore which is absorbing, or maybe 10 chromophore which is absorbing here, 10 more which is absorbing there, and so on and so forth. So it's basically, you know, they get united and work together to have that spectacular property.
Certainly. Thank you. Next, an audience member is curious about the term being used, photoprotection, and they are asking what exactly it entails and or what physical or chemical property is being referred to when we say the photoprotection property of melanin.
Photoprotection means, let's take the example of melanin. Melanin is some kind of a heterogeneous polymer, right? So light shines on that heterogeneous polymer, and yet the integrity of that melanin remains. As you can see, I mean, our skin don't get degraded when I go out in the sun. I mean, I shouldn't go out in the sun, in very direct sun for too long. But even if I do, I just get sunburns. I don't get strange products in my, you know, in the melanin structure, which can lead to other harmful products. So the absence of product formation, you know, in that potential energy surface, if I think, absence of product formation would be protection. So if it comes back to where it started from.
Thank you. That certainly clears it up a lot. And next question, very related, is audience member is curious, is that if melanin can indeed protect us from the sun, why do we require additional sunscreen protection?
This is a very good question. It does protect us from sunlight to a large extent. But as you saw in that closed loop structural stuff, all the reduced products are going towards the oxidized products and cycles between them. But I haven't been, at least in our studies, we haven't been able to see how the oxidized products would come back to the reduced forms. And maybe that's why, you know, when people get older and older, they get those age spots and stuff like that, and oxidized. And that's why you have all these different cosmetic products even to remove that oxidation. That's my feeling. I'm not a biologist, but that's why I think you would need some extra protection, especially if you are in the harsh sunlight.
Thank you, Professor Ghosh. And actually, that also kind of answers another related question we had. But if you would like to add anything to it, I will still ask it. Does age have an impact on the photoprotective properties of melanin in the skin?
Yeah, it does. And actually, what has been known from experiments is that as if you compare aging skin with young skin, they have a different, somewhat different chemistry. The oxidized is to reduce that ratio changes. And as it becomes more and more oxidized, I guess the capacity to self-heal and protect and all of that kind of reduces a bit. Of course, there are some people who are blessed with fantastic skin. So that's just the diversity among people. But on an average, with aging skin, that's what happens. Another point I would like to make, since people are asking about sunscreen, many of the sunscreen molecules itself also use this kind of a cis trans isomerization to quench the light, as in it will absorb and then goes, there's some cis trans isomerization and sometimes even degradation products. That's why for sunscreen, you have to keep applying. You can't have one sunscreen and you are good to go. That never happens.
That makes sense. That's why we have a degradation effect there rather than just photoprotection, which is why we need to reapply every few hours. That is very interesting. Thank you, Professor Ghosh. Next question is, how do the enzymes in vivo conditions affect the photophysics of melanin and particularly the self-protection part?
You are asking very difficult questions for me. So yeah, again, I'm no biologist. I know of the ways that a melanin is formed in a melanosome. That's the organelle where the melanin is formed. And even that is driven by sunlight, in the sense that if you are exposed to sunlight more, then more amount of melanin is formed in the melanosome, and therefore you have more protective capability in your skin, which is why, if you are thinking about the people near the tropics and the equator, you have darker skin and so on. But yeah, the specific which enzyme leads to what, sorry, you have to ask a biologist, not me.
Thank you, Professor.
Sorry to interrupt, Dr. Das. Since we have a lot of questions pouring in, but due to the paucity of time, we can take a couple of more questions.
Sure.
Thank you.
Okay. I will ask this one. An audience member is asking about a little more insights into the inverse learning technique that has been used for the modeling of the melanin spectra and what data sets it has been trained on.
Thank you for this question. I didn't have time, that's why I didn't go into the details. So essentially what we have done is, to begin with, we have created these different tetramers of from the melanin monomers. And from those tetramers, we have created a library of this molecule gives this spectra and that molecule gives that spectra, like that. And in different parts of the spectra, we have trained different models to say, now that we have the, for a few of the molecules, we have a structure to spectra correlation, what is the one to go back? As in, now if I give the spectra, what structural parameters does it give out? And the structural parameters that we mainly focused on were where the molecules are attached and what are the angles and so on. We didn't look at all structural parameters because then our output size is too large to predict. So those are only the few output that we could predict, and that's what we did.
I'll maybe ask this one. And in your opinion, since this is kind of the current trend and the rage now is artificial intelligence, and how do you think it could be in assistance in such studies, if it can, especially predicting and understanding molecular structures? Your two cents on it.
Yeah, there's a lot of effort being going in that direction, building the full chemical space, then, the chemical space constrained by certain constraints. And then for predicting molecules that are best suited for certain properties and stuff like that. So there's actually been a lot of successes in those directions. So that's great. But still, in some way, where we need to improve is to have more accuracy. So because machine learning by itself or artificial intelligence by itself has many a times large error bars, and the error bars are because the data sets we are training them on are fairly small. And the reason we have small data sets is because we could run the experiments or the computation only on a few of the systems. So it's kind of an effect of that, that the errors are still higher than chemical accuracy, I would say. But once we keep building these databases or even better algorithms to train things with lower amount of data, I think we have I'm very optimistic in this direction.
That's great. So finally, thank you, Professor Ghosh, for answering all of our questions. And we still have a lot more, but I'm sorry we could not pick up everything. But in the interest of time, we need to close this session at this point. And before ending, please share with us if you have any concluding remarks, after which I will hand over the stage to Neha for closing.
Yeah, as a concluding remark, I think, well, computational chemistry is a fantastic new direction for it has been used to study ground state for quite some time now. In the direction of excited states, it's still not so common to use computational chemistry, but it's picking up, and that's why it's an exciting direction. That's the remark I have. And I would also like to see that there's a lot of people who said hi to me or thanks, or I couldn't read all the messages. So thank you all. And thank you for being so interactive. I had a great time.
Us too. This was a great session. So off to you, Neha.
Yeah, thank you so much, Sharmishta and Reshmi and Professor Ghosh for this wonderful Q&A session.